Hi, Mr. Cohen, can you hear me?
Yes, I can. How you doing, Connor?
I'm doing all right. Been spending some time reviewing this material for the exam this weekend, and I feel actually pretty decent at this point with the Raymond sums. So I was going to do some optimization and I guess review the U subs because feels like that kind of slipped my mind a little bit, it seems like. So anyway, I was working on these problems. I can find them. There we go. So this is so it's the integral with the function, and it's an indefinite integral. So with the function, it's a rational function. So the numerator is parentheses the square root minus 1, and that whole term is squared.
Hold on 1 second.
Yeah, hang on. Okay, so I'm sorry. So it's the top half of it is in parentheses, and it's the square root of x minus 1 quantity.
X, I didn't hear that first.
Yeah, no worries.
Okay.
Okay, and then that's all over the square root of x, and just note that that 1 is not in is not part of the square root.
So it's the square root of x minus 1 all squared.
Right. Yes. So I don't know if it was helpful. I'll explain my process here, what I tried to do. And I guess to clarify, what would you make U for? Would it be the top, the numerator? Or
This is really not a U substitution problem.
Okay.
This is a straight polynomial problem. So if we square the top, what do we get?
1 minus, or x minus 1. Sorry.
No, x minus 2 root x plus 1. Correct? Unless I've written it wrongly.
Okay.
In other words, if we're squaring square root of x minus 1 times square root of x minus 1, that is x. That's minus 1 square root of x. That's another one. So that's where I get the 2 square root of x, and then minus 1 times minus 1 is plus
1. Okay.
Okay. And all of that is over square root of x. Now, because we have a single entity in the denominator, we can separate this into 3 fractions. There's that fraction, there's that fraction, and there's this fraction. And all of them can use the power rule. So what's the first fraction?
I guess that's x over square root of x.
Which is x to the 1/2. Right?
Okay.
In other words, x to the 1 over x to the 1/2 is x to the 1/2. Minus the integral of the second one. For some reason, we had a power outage today. My computer seems to be reacting to it. What's that? The middle fraction?
That's negative 2 root x over square root x, which is negative 2x 1/2.
Just negative 2.
It's negative 2. Okay.
In other words, this cancels with that.
Gotcha.
Plus, and the third one?
So this is 1x to the 1/2.
1
This is
over
x.
x to the 1/2, which let's make it look like this. You always want to put the x in the numerator.
Okay.
So what we were looking at boils down to this. What's the integral of x to the 1/2? Add 1 and divide by the new exponent.
Okay, yeah, so that's 2/3 x to the 3
Hold on.
halves.
Add 1 makes it that.
Right.
Divide by 3/2 is the same as multiplying by 2/3.
Right.
Okay. And then what's this one?
So that's, we add to the power, so that's just negative 2x.
Yeah. I think I got too many negative signs here. I think that should be like that. So it's just minus 2x. And the third one,
Okay, so this is just 2x to the 1/2 then?
well, let's start. Yeah, you kind of get ahead of me when you give me the coefficient first.
Okay.
I just don't think of it like that. I mean, that's, if you can do that, that's fine. But I add 1. That's where I start. And then I divide by 1/2, which is the same as multiplying by 2.
Okay.
Plus c. Now, each one of them have a plus c in them, but they can all be added to this plus c. In
Okay.
other words, this plus c is all of the c's combined.
Why do you need a c for indefinite integrals?
Because they're indefinite. In other words, if they're definite, you would not have a c. But if they're not, in other words, here's the thing. If you were to differentiate this with the plus c, you would get what you started with.
Okay.
If you were to differentiate it without the plus c, you would get what you started with. So the answer is these first 3 terms plus any constant at all will result in the derivative being that.
Okay.
Okay. And let's see, can we do anything with this? Doesn't look like
all
we
that my
can.
professor is gonna want from me.
Yeah, no, we
So,
can't. We can't add x to the 3/2 to 2x to the 1/2. If we were multiplying, we could, but that looks like a final answer. And my guess is that you will lose points if you omit the c.
yep.
You always have to put the c in. And in fact, can I erase this?
Yeah, you can raise it.
I read an interesting novel about time travel. And a guy went back to the past, 1900, when calculus was first being taught in Britain. He got a job, and this was the question. What is the integral of e to the x? What's the answer?
The same, right?
No. That was the whole point of the inclusion in this book.
Oh.
He said most students will say e to the x. The ones he wants will say e to the x plus c. If you differentiate that, you get e to the x. Therefore, the integral of e to the x must include this c, because there's literally an infinite number of answers to this problem right here. And that includes all of them right there. But it can be any c you want. which means there's an infinite number.
Okay.
Because of the derivative of a constant is 0. All right. What else do you have, Connor?
All right. That wasn't a U sub problem. I tried to solve that with U substitution. So that was
Yeah,
just how I
sometimes
approached it.
the thing about U substitution is don't use it unless you have to. In other words, if you can turn something into the integral of 3 polynomials and you can use the reverse power rule on each one, like I did there, then you don't need U substitution.
Okay.
And in fact, it wouldn't have been helpful if if it was x minus, no, it was x squared minus 1 squared. No,
X
square.
root x, yeah. Root x minus 1 squared over x squared.
All over x?
Root x, yeah.
Root x?
Yep.
So the pattern, or I mean, you might be able to use U substitution here. Now that I look at it, I think you probably could. But it's not necessary because I can square that and then I can work with 3 separate fractions, the integral of each one of them. Now it'd be a whole different story if the denominator was a binomial term. Then you couldn't do that. In other words, the one I've constantly given you is this one. Notice the binomial term is, or the denominator is a binomial, so I cannot separate this into 2 fractions. Always look for the easiest way first.
So to push back a little bit, if this had been the exact same function, except that the numerator was c to the power
Yeah,
of
then you'd need
27.
U substitution. Yes.
Okay. Okay. So it was because this was a relatively simple problem.
Yeah, this actually can be solved without U substitution.
Gotcha. Okay.
But certainly if I was going to do, I could solve this with U substitution, letting U be whatever's inside the parentheses in the numerator.
Okay.
And then figuring out du dx. And yeah, I have a habit of not writing that in there, and that's probably not a good habit. You should always have that. Because if that's something other than x, let's say that's a dr, you can't do this problem. This has to match the variable of the integral. Okay. And that's why when you use U substitution, you have to get the whole thing transferred into an integral of U. And there can't be any x's left over. Now, if this problem was given to you and it said use U substitution, we could do it. I can do it if you like, but I'll leave that up to you.
Just tell me so the U would be root x minus 1, or would you put it in parentheses?
No, you're exactly right.
Okay.
Because I want this to be U squared.
Okay. Okay.
Okay, so U is equal to, and then always remove your radical signs. And then figure out what the derivative du dx is. Okay. And it's 1/2 x to the minus 1/2. So I can take that dx, put it up there, and then I can solve for dx, which becomes 2. Let's see, I have to divide both sides by x to the minus 1/2. So that minus 1/2 goes in the numerator. I think I did that arithmetic correctly.
And I'm sorry, what are you, so you're getting everything on one side there? Is that the idea?
When you use substitution, the very first step should be figuring out what du dx is.
Du dx. Okay.
In other words, the first step is really taking the derivative. And that's very common in integral calculus, is the first step is taking the derivative.
Okay. Okay.
And yeah, I'm going to be dividing by an x to the minus 1/2. So I think this is correct. So now my goal is to rewrite this integral as an integral in u.
Right.
So the first step is u squared. And let's just go ahead and leave that in there. And then for dx, let's put this. 2x to the 1/2 du. And now notice the x to the 1/2s cancel, and you have an integral, a perfect integral in u.
Okay, so it's fine to leave for a second there, it would have looked like you were about to have a multivariable integral. But it's fine so long as you
Right. And the whole point of u substitution, when it works, when there is a pattern recognition, in other words, when one side and when one part of the integral is the derivative of the other, then the second variable disappears. Notice that the x to the 1/2 cancel. That will always happen. If it does not, then it is not a u substitution problem. It's some other kind of integration problem.
Okay. So it's not necessarily bad to have what you would have had in, like, I don't know if you'd call it.
No, I mean, they kind of teach it in a slightly different way where I really don't like the way it's taught. It does save a step, but it makes it harder to understand what's going on. To me, if you just do straight u substitution and go that step and that step and that step and that step, and now wherever you see dx, you can substitute 2x to the 1/2 du. And so I did that, 2x to the 1/2 du, and that got rid of the x's, because the x to the 1/2 cancel with that x to the 1.
Okay.
And that always happens as long as it is a u substitution problem.
Okay.
If it isn't, then you have to use a different technique, which you haven't learned yet. So everything they're going to give you is going to be u substitution, or something you can turn into, like I did the first. In other words, I didn't need u substitution for that. It's all I needed to do was convert it to, I needed to expand that and then convert it to 3 fractions and the integral of each fraction. I could use the power rule, the reverse power rule. So u substitution was not actually needed here unless they specifically ask you to use it.
The section says to use u substitution. I mean, I guess I would agree with your point that it's not necessary. You know, when we did this the first time, that made sense. So anyway, I there's another problem that I wanted to try then that I think will involve u sub.
Okay.
That might teach the fundamentals here more importantly. So this is a definite integral. It's from 0 to 1. And the function is x over the square root of x plus 1. So this is all part of the square root now.
Like that?
Like that, dx.
All right.
And it gives a little detail. So
Now, this looks like a change of variable to me. It does not fit pattern recognition because pattern recognition would require that the derivative of the inside is equal to x, and it's not. So this automatically looks like u substitution change of variable. So what are we going to let u equal to?
X plus 1 to the 1/2. Or does
No,
does it just stay
no,
outside?
just x plus 1. It's just what's inside.
Gotcha. Okay.
Okay, and now what's the next step?
To find the derivative for dx du.
So what's the
du
u dx? Not dx du. What's the u dx?
1.
Which makes du equal to dx. Right?
Right.
Okay, so now I can rewrite this thing. And instead of x, what is x equal to? U minus 1. That's the part that's different. Is you have to do that little extra step where x equals u minus 1.
Okay, okay.
And that's how I get rid of the x. And then that's the square root of u. And du is dx. And so now I have something that is an integral in u, totally. And I haven't changed the limits of integration yet, because I actually prefer to do that at the end. But notice the difference between what I'm looking at there and what I'm looking at here. The difference is the denominator is a single entity. So I can split this up into two fractions. I cannot do that to the top. In other words, in order to split up two fractions, let me lay it out simply. A over b plus c is equal to a over c plus b over c.
Okay.
But a over b plus c, that is definitely not equal to a over b plus a over c. In other words, you cannot do that one.
Okay.
Because it's got a binomial term in the denominator. So the only one you can do is this one. And I have to use u substitution in order to get it into the form of that second one.
Gotcha.
So now what's the next step? What's that equal to?
So now we can say u minus 1, and then we can rewrite that denominator as u to the negative 1/2, right?
Actually, if we're going to rewrite it, let's write it as u to the 1/2. That's what it is, as long as I'm going to leave it in the denominator.
Okay, so we still have a rational function.
Yes.
Okay.
Yeah.
All right.
There's no difference between square root of u and u to the 1/2. The difference is calculus doesn't like radical signs. You always convert a radical sign to an exponent because calculus likes exponents. When you're doing integrals, you're doing power rule or reverse power. So now that I've eliminated the, what's that fraction going to be? What's u divided by u to the 1/2?
Okay. Okay, yeah. So yeah, u divided by u to the 1/2. And then this would be,
in other words, the second fraction is that one.
And why is it to the negative 1/2 now for the power?
Because it went from the denominator to the numerator.
Okay.
In other words, I had 1 over u to the 1/2 as my second fraction. That is equal to u to the negative 1/2.
Okay.
Okay. And now it's pretty easy. We can just use the power rule. What's the integral of u to the 1/2?
1/2 is, let's see. So that's going to be 2/3 the power. So, or no, 3/3 of the power. So 1/2
See,
plus.
I think you're making a mistake by figuring out the coefficient first.
No, I'm not. Well, hang on. So the power is going to be 3/2.
Okay.
3/2.
Now divide by the new power.
And then, so that will be 3.
3/2 in the denominator, which is the same as 2/3.
Okay.
Okay. And then do the same thing for this. Start with the exponent, always.
So that's the power now added by 1 is a 1/2. And then that's, so divided by 1 is the same as 2.
Dividing by 1/2 is the same as multiplying by 2. Now, I can either do this by figuring out what happens to u when x goes from 0 to 1, and it looks like u would go from 0 to, or from 1 to 2. So if I wanted to change my limits of integration, that's the way I would do it. If I don't want to, then I go back and I substitute for x before I evaluate. And you see where I got the 1 and the 2? In other words, if x is going from 0 to 1, then u is going from 1 to 2. Upper right.
Mm-hmm. And, oh, because we're plugging in for.
Yeah. In other words, if we're going to do this thing in u, then we need to figure out the limits of integration in u.
Right. I'm just trying to figure out why we're doing it by 1. Because x is just 1.
Well, x goes from 0 to 1.
Right.
And when x is 0, u is 1. When x is 1, u is 2.
Ah, okay.
Okay. So you could do it like this, and that will give you the same answer. Or you could do it by going back and substituting what u is. Well, u is x plus 1 to the 3/2, all divided by 3, minus 2 times x plus 1 to the 1/2. And now I can use the original limits of integration, which actually might be a little easier.
Right.
And I've always found it to be easier. So I generally resubstitute before I evaluate. And you know how to do this?
Yes. In fact, since it's from 0 to 1, this would be easier.
Yeah, it is a little
have to
bit.
worry about 1 essentially.
Yeah, exactly. 1 to the 3/2 is 1. 1 to the 1/2 is 1. So it's actually quite a bit easier if you evaluate it in x, as opposed to figuring out what 2 to the 3/2 power.
Right.
So I would always go that route. resubstitute before you evaluate, and then you don't have to go back and figure out what the new limits of integration are.
Now I'm probably overwhelming myself because I've been trying to go back to the unit, but I asked my professor about this and she prefers, because it sounds like in Calc 2 with other integration techniques, in U sub you can go back to evaluating at the original bounds, but in other types of integration, it sounds like you can't. So she wants us
Yes,
to.
I have seen there is a page in my calculus book that gives a problem that is better analyzed if you change the limits of integration, but not quite sure why. And I've never seen any other problem like it. So it's perhaps in more advanced calculus there is, but in the calculus you're taking, I'm willing to bet that you could always resubstitute for X before you evaluate.
Yes.
And you can see that it is a little easier because 1 to all these powers is just 1. So this answer becomes 2/3 minus 2. I guess there's a little bit more to it than that, but let's see. If I substitute 1, yeah, it's a little harder than that. It because it's going to be 2/3 of 2 to the 3/2 minus 2 times 2 to the 1/2. And that whole thing minus, when you substitute 0 for that, you get 2/3. And when you substitute 0 for that, you get 2. And that's actually in parentheses. And so that would be the answer. And you can get that in one of 3 ways. We can get it without using U substitution at all. That's one way. That, to me, that's the simplest way. If you can always avoid U substitution, it's better. If you can just chop it up into a polynomial. Actually, this one we can't. Yeah, I was looking at a different one. So this one does require U substitution because I cannot chop that up into 2 fractions. So there's really only 2 ways to do it. There's evaluating it after substituting the original U back in at the original limits of integration, and there's this way over here where you, or there's this way rather, where you substitute it with the new limits of integration.
Right, right. Okay. So I'm going to mix it up now and head to, actually, I guess conceptually, Mr. Cohen, just so I'm walking away feeling confident about this. Do you have anything offhand that would be a good example of showing when you need to use U substitution?
Yeah, the ones we haven't covered much are pattern recognition. Notice why this is a pattern recognition problem. What's the inside?
X cubed, right?
So the first step, what's du dx?
2x, no, 3x squared.
The fact that that's an x squared and we have an x squared there, the 3 we can handle. The important part is that the exponent be the right power.
Okay.
And if I go ahead and solve this, it would be du equals 3. And this is actually the way I prefer to solve it. Solve for dx. You get du over 3x squared. Now go back to your integral and substitute and leave the x there for the moment. This is definitely the sine of u. And I need to substitute something for that, and that's going to be that. So that would be du over 3x squared. Notice the x squareds cancel. And I end up with the integral of sine of u over 3. I can take that 1/3 out. So this becomes 1/3 times the negative cosine of u plus c, if it's an indefinite one.
Okay, I gotcha.
And then that would become negative cosine of x cubed, if I go back and resubstitute what u is.
Okay.
But the trick is to always recognize that this part of the integral is in some form the derivative of what you're going to let u equal to. Doesn't have to be exactly. In other words, the derivative was actually 3x squared, but it has to be the same power. If this was 2/3, this u substitution does not work.
Gotcha. Okay.
So it's only going to work on certain integrals where you basically have multiplication going on, and one of the products, or excuse me, one of the things being multiplied is the derivative of the inside of the other thing, or close to the derivative, the same power as the derivative. Another example might be okay.
Okay.
So what you should see when you look at this, first of all, I cannot perform this multiplication. So I cannot turn this into a single polynomial that I can just use the power rule on. But what I have to recognize is that the derivative of the inside is x. Okay. This x right there.
Right.
So this is a composite function that if we had the solution would be taking the derivative of the outside times the derivative of the inside. This is basically the chain rule in reverse.
Right. I remember you saying that.
Yeah, that's the way to kind of think about it. And only for pattern recognition, not necessarily for the change of variable. The change of variable is a little different. That is not the chain rule in reverse. But when you have g prime of x times f prime of g of x, that's the pattern you're looking for. This is g prime of x.
Gotcha. Okay.
And the best way to do these is just to do a number of them and you know, do 5 or 6 of them and learn to recognize, because pattern recognition is exactly what it says. You have to recognize it because at some point in calculus, you're going to have 5 or 6 different techniques you can use. And you have to know which problem uses u substitution, which problem uses the reverse product rule, which problem uses trig substitution. There are literally 8 to 10 different integration techniques, depending on the formula or the function that's being integrated.
Okay. Okay, noted. That was helpful. That was good.
Okay.
Okay, so I'm gonna switch gears now to optimization.
Okay.
If
we haven't done very many of these. Okay.
No, and I mean, honestly, until recently, I was kind of hitting the stride and doing these okay, or doing most of the work in class good. I'm probably gonna have to send this in chat because it's hard to explain. I can try if you'd like, but it's probably gonna be easier to send a
I
picture.
can give you also the most basic one, optimization problem, the
If it's
one they give everybody
if
to
it's
start out.
squares, if it's anything with squares, I'm comfortable with the squares. This involves trig with angles.
Okay, let's do this one. Go ahead and send it to the chat room.
Okay, yeah.
Yeah, the
Most of
most
the
basic one is where you start with a rectangle and you try to turn it into an open top box by cutting
yes,
out
yes.
squares out of each of the corners.
Okay,
And the
so
problem is, how do you make a box that has the maximum volume? Whenever you see the words maximum or minimum, you're talking about an optimization problem.
right.
Whenever you see the words rates, you're talking about a related rate problem. And those two are really covers all the word problems in differential calculus. It's either an optimization problem or a related rate problem.
Yeah, I think it's. I should have been sent to you in
Did you
the
send
chat.
it to my email or did you drop it in the chat?
I dropped it in the chat
Okay. Yeah.
on Zoom.
Where's the chat? Hold on. There
I
it is.
can email if
No,
it's
I can
easier
see
for
it. No,
you.
I got it.
And I got the answer for this, but I got the answer for this online. This is one of the tougher problems that was in
Yeah.
the homework. Um,
Okay. I think you can kind of see why, if you had a longer pipe, it wouldn't fit around that corner.
right.
You make that pipe 50 feet long, no way you're getting it around that corner. So there is a maximum length pipe that will be able to turn that corner. Let's see. All the information is written on the diagram, it looks like. Yeah. All right. So when you are optimizing, you want to figure out what is it that you're optimizing. Well, we're optimizing the length of this line, right?
Okay.
And we need a formula because if we can express the length of this line in terms of theta, then we can optimize by taking the derivative of it and setting it equal to zero.
Right.
That's the whole thing of optimizing. Now, the question is, what is the length of this line?
I mean, so they give you the length of the hallways, relative to that corner. So it's got to be something with that.
Yeah, let's see. Let me think about this for a second.
So like this might be maybe too generic, but like, you have the length of something, which would be x plus y, maybe.
Well, the problem is we don't know that point. We don't know that point. So we want to come up with a function of theta. There's no other variable here. This is not an x variable. We need the function defined in terms of theta. and then we can optimize. Now, the question is, think about this for a second. If I draw a line like this, then I can say that the sine of theta equals 9 over x. Trying to think about this.
So quick question, if I may, maybe to challenge you a bit on this. Why do we want this in a function of theta? Why not something in a function that contains theta, which you would take the derivative of?
Well, that's why we need, if I can define it as a function of theta, then I can take the derivative of it, d theta dt, or excuse me, d theta dx. So actually that gives me an idea. The length of this line, let's call that x. And we want to maximize x.
Okay.
Right? In other words, what's the length of the longest pipe? So we need the maximum x there that will fit this model. Wow. For some reason, my mind is not coming up with a function. Let me think about this for a second. Trying to figure out if I were to redraw this, whether that helps. In other words, what if we start with that being x? But now we don't have any way. Do you have any tips at all on this, or do you just have this final answer here?
I mean, yeah, I can look up where I got this from again real quickly.
I'm a little stumped as to what the formula that we're wanting to optimize is. And it needs to be x, because if we can get x equal to something, then we can take the derivative of x and set it equal to 0. So x needs to be a function of theta. Question is, what function?
Okay, so this is how someone did it online. This isn't quite, this is mostly the same work that I remember seeing. I got this off of a different website. But
okay.
So what they did is they have this done a little differently now, where if you were to take the image of you know what the diagram is, from the corner of that that inner hallway, I guess, right? You would draw like a dotted line up. So where that.
So you're talking about like this?
Nope. From that center, like from where that corner line is, where the blue line.
What corner? Touches, I'm looking at a lot of corners in this.
Where the blue line touches, there's that center, like inner hallway corner, right?
Right here?
Right there. They draw up a a straight dotted line up to the top.
Okay.
And then from there, 1/2. So now, you can kind of picture two triangles, right? So one triangle on the right side of the dotted line, they have listed as Y, and the other side where the theta is drawn, they have listed as X.
Like this?
Yes, like that.
Okay, and then let me get rid of that X because it's confusing now.
So
Okay.
you could, if you wanted to, I don't think it's necessary, but from the bottom of where that X, and the theta is, they draw a dashed line to visualize another triangle.
But a horizontal.
Yes, like that.
Okay.
So now they have L of theta equals X and plus Y, which equals 9 over sine theta plus
Hold on. Start again. L of theta.
L of theta is equal to X plus Y.
Now, how do they get that? The length of theta?
The Yes,
Okay, all right.
well, because we have
Except that's not theta. In other words, theta is that angle.
right. So that
This is 90 degrees minus theta. And I do know this measurement. So I could say that the cosine of 90 degrees minus theta equals 9, the adjacent, over the hypotenuse. So I can come up with that equation given what you've given me.
Right. And let me continue on here, because that was where we have L of theta equals X plus Y.
Okay.
They have another equal sign to that. So
Okay.
continuing on the same function, if you will,
Uh-huh.
is 9 over sine theta plus 6 over cosine theta.
Okay. I think I can figure out where they get that.
Okay.
If X is this part, then it's 9. In other words,
So it's opposite.
sine of theta is going to be 9 over X. So X is going to be 9 over sine theta. Okay, so I get that. In other words, based strictly on this triangle right here, the length of X, or it's actually the sine of 90 degrees minus theta, is it not? Hold on, maybe I'm drawing. I might have drawn this thing wrong. Let me draw it probably the way they did it in your example, like that. And that is 9. So I would definitely be able to say the sine of theta, if that's X, equals the opposite, 9 over X. And from that, I get X equals 9 over sine of theta. So I get that one. Yeah, this is definitely what we need here. Okay. And on the other one, the other triangle, let's see, Y, if that's theta, then the cosine, is that theta? No, that's not theta. In other words, this is 90 degrees minus theta. So that's a vertical angle. So that's 90 degrees minus theta. And then you would have cosine of 90 degrees minus theta would equal the adjacent, which we don't know. The cosine of 90 degrees minus theta is the same as sine of theta, so trig identity. And the sine of theta is, hold on. I'm just about got this figured out. How do they get that for y? In other words, y is the sine of theta. Let's work with the problem is this angle right here is not theta. In other words, if we look at this first triangle right here, this angle is 90 minus theta, correct? Because it's a right triangle.
Okay.
And if that angle is 90 minus theta, this is a vertical angle, that's 90 minus theta. Unless I'm not seeing it, but I'm pretty sure I'm seeing it correctly. So now we can say in this second triangle that, let's see, I know what the opposite is, so it would be this. Okay, now I get it. So it's the sine of 90 degrees minus theta is equal to 6 over y, which makes y equal to 6 over the sine of 90 minus theta. And the sine of 90 minus theta is the cosine of theta. So that's how they get that.
Okay. Okay.
Okay. It's a little difficult, but now I understand how the length the length of this steel bar as a function of theta is clearly x plus y, and x is 9 over sine theta, y is 6 over cosine theta. So the length function is what we're trying to optimize. So we want L prime of theta, and that is going to be nine cosecant theta. First of all, no, not with the prime, without the prime. In other words, I'm trying to write this with these trig functions in the numerator.
Okay. Okay.
And that you need that because I don't know how to differentiate trig functions in the denominator. And this one is 6 secant of theta. Okay, so you agree that that is the same as what I've written?
Yeah, because you took the co-functions of those, right?
I took the reciprocals because they're both in the denominator. I need the reciprocal. The reciprocal of sine is cosecant. The reciprocal of cosine is secant.
You refresh my memory. I guess the co-functions and the reciprocals are not the same thing.
No, not at all. Okay. Here, let me write it all out and then I can erase it. Sine theta, the one to really start with is cotangent. And I'll explain why. What's the reciprocal of cotangent?
Is tangent?
It's 1 over tangent.
1 over tangent.
That's the easy one. That's always the case. Cotangent goes with tangent, whether you're talking cofunctions or reciprocals. Cotangent and tangent go together.
Gotcha. Okay.
So the two that you have to figure out is what is the reciprocal of sine And that is 1 over cosecant of theta. And the thing I know is that that is always a different letter than that. In case you get it mixed up and you want to put secant in that denominator, it's never that. And therefore, cosine is the other one. It's 1 over secant. And again, remember that letter is not the same as that letter. So you know you got it right.
That's what I was thinking of the co-functions for, but I see now.
Right. But the cofunction of sine is cosine. It's not cosecant.
Gotcha.
And the cofunction of cosine is sine. So cofunctions and reciprocals are not the same.
Noted. I just Googled it too. That's correct. So, okay. That's
okay.
I follow what you did.
Okay. And
now,
is all I've done is converted the sine in the denominator and cosine in the denominator to in the numerator.
Right. We've gotten rid of our rational functions, basically.
Well, I don't know how to differentiate these when they're in the numerator. And I do know how to differentiate them when they're in the denominator. So the derivative of this function is, what's the derivative of cosecant of theta?
You gave me this once. Hang on, I have you saved. Calc trig. Is this it?
Well, let me think.
Yeah,
first.
so hang on. So the cosecant, right, is negative cosecant x cotangent x.
Right. Only theta.
Only theta.
And then this one is 6 times
secant of theta times tangent of theta.
Yeah. And notice that this one is always negative when you're doing the derivative of a anything. In other words, I was doing the derivative of cosecant. So the answer is negative, first of all, and it's cosecant cotangent, where the derivative of secant is positive and it's secant tangent.
Okay. Yeah, that makes sense.
And now what I want to do is set this equal to 0.
All right.
Now, the question is, can we solve this? Let's see. What is the length of the pipe? So assuming that I could put this into Wolfram alpha, this bottom thing on the right, and it would tell me what theta was. There's only going to be one theta that works here. And then I could go back to my original function and substitute that theta and come up with the length of the pipe. So can I solve this thing myself? Without me wasting more of your time, let me use Wolfram alpha to solve it.
Hey, I'm typing it in too to see what it.
Yeah, you can try to solve it if you want. Also,
we're solving for theta, right?
Yeah, we're solving this bottom right for theta.
Okay, so
and the easiest way I have of doing it is to go into Wolfram alpha.
Let's see what Wolfram says, but I'm getting 0.5030, so on and so forth.
And that's going to be in radians.
Yes. Yeah. Plus pi n. So yeah.
Okay, I'll go with your number. And now can you figure out what 9 over sine of that number is plus 6 over cosine of that number? And it should be this answer that you have down here, which is what, 21 point something?
Okay, so 9 over the sine of that number.
Yeah.
All right.
What was your number again for theta?
0.50308978.
Okay, we want to make sure it's an acute angle. And an acute angle would be anything less than pi over 2. So anything less than 1.5. Yes. Okay. So that is less. Okay. So it appears that we have a theta that at least makes sense. And now if you can come up with what 9 over sine of theta is plus 6 over cosine of theta, it should equal your 21 answer.
Huh. I got
Doesn't?
25.
What's that?
I got 25.5.
And let me stick this into Wolfram alpha. Let's see what
Yeah.
happens.
You're going to stick the derivative when you set it equal to 0, right?
Yeah, here's what I'm going to do. Wolfram alpha. I have to save this because I don't have this one stored on my computer. Let's see. Usually it takes me straight to where I can input a function. Huh. We've changed this a little bit. Calculate a derivative. We don't really want to do that. Simplify an expression. Wow. Didn't realize I was going to solve an equation. Let's try that. Wow. Hold on a second. I got to get to Wolfram alpha.
I was going to say back out to the to your search.
Let's try calculus and analysis. Let's see if that changes. Nah. We used to have a single equal sign, and you could put in any function and it would solve it.
Yeah.
Maybe I can do it up here. Yeah, I think I can. Let's see. So I want -9 cosecant of theta. Theta has to be spelled out here, I think.
Oh, wait a minute.
Plus
I made a mistake on my end.
6. No, whoops, hold on. Times cotangent of theta. And that is equal to, no, this isn't going to give me the answer, I don't think.
-9 cosecant plus 6.
Yeah, maybe if you can do it, go ahead and do it, because I'm having a little problem with Wolfram alpha here. On figuring out how to put this in. What happens if I click this equal sign? No, this might do it. Oh, here we go. I got it. So I want that to equal negative -6 secant of theta times tangent of theta. There. Is that correct? 9 cosecant theta cotangent theta equals, and when I move the 6 over to the other side, it becomes negative. So it's -6 secant theta tangent theta.
Yeah, that's correct.
Okay, so it shows me what my input is, which is correct. See where it says input?
Mm-hmm.
And then it's going to give me my answers. And I get,
I was gonna say, I was gonna ask why you set it equal to -6, because I thought we were taking that whole term and setting it equal to 0.
we are. And when you do that, you move the 6 on the other side. So you get -6 secant theta tangent theta equals -9 cosecant theta cotangent theta.
Okay. Let's see if I can match what you're getting. So we should have negatives on both sides of that equation, right?
Yeah. And it looks like this is our answer here. Down here, in other words, these ends are, there's multiple answers, all 2 pi. There's your 2 pi n right there. So the theta answer without the multiple looks to be 2 times that.
826,385.
So that would basically be 8, 4. We're in radians. We're still under 90 degrees, which we want. And now plug this in, 0.84 radians. Let's make it 5. It's closer to 0.85 than 84. Into this equation to figure out what x plus y is.
Yeah, that's it. Okay. How did you get the conversion for the radians there?
Calculus is always done in radians, never in degrees. So I know that when I solve this equation, my answer is going to be in radians. And I got that answer by taking the 2 pi n out and multiplying the 2 times the 0.42
okay.
to get 0.85. And now what we need is 9 divided by the sine of 0.85 radians plus 6 divided by the cosine of 0.85 radians. So if you can come up with a number on that, that should be your, what was it, 21?
Yeah, no, it is. It is. That's
wonderful.
This is
wonderful.
Yeah.
So this was a hard problem, really a hard problem.
Well, Mr. Cohen, so the last exam, I butchered the first exam because of technical difficulties. She gives you a fake test to take, and I took it, and you can do it again until you get comfortable with the format. Somehow it automatically put me into the real exam. So I butchered that one, but she gave me a reprieval on it. The second exam was really tough. I mean, and as you've seen with some of the homework questions, these are really tough questions.
Well, this is one of the hardest ones I've seen. I'm not sure I would have been able to do this without your help getting started. And no, seriously, and just you just kind of have to get used to some of these. But first of all, I would not have been inclined to use 2 variables because we're doing single variable calculus. But I guess that's the only way to do this. And then you have to draw lines, dotted lines, to define theta in terms of x and y. And you have to realize that that angle is 90 degrees minus theta, because all right triangles, if that's a right triangle, the 2 acute angles are always theta and 90 minus theta. And if that's 90 minus theta, that's 90 minus theta.
Okay.
And now you can write equations for the length of theta. In other words, if the length of as a function of theta is equal to x plus y, that actually doesn't make any sense, because when you say the length as a function of theta, you're supposed to find nothing but thetas on the other side. But we can convert that x into a theta. because we know this distance right there is 9, and we know that the cosine of theta is 9 over x. Therefore, x is 9 over cosine of theta.
Sine of theta, right? Sine of theta.
It's the cosine of theta. Yeah, the opposite. Yeah, 9 over sine of theta, excuse me. And then this one is 6 over cosine of theta. And you actually, this becomes sine of 90 degrees minus theta, but that's the same as the cosine of theta by the cofunction identity.
Okay.
Okay. In other words, the sine of theta is always equal to the cosine of 90 degrees minus theta. The secant of theta is always equal to 90 degrees minus theta, or the cosecant of 90 degrees minus theta.
Yeah.
So when you have a 90 minus theta, you can always convert it to its cofunction. And that's how I get that. Because that also gives me the sine of 90 degrees minus theta is 6 over y. And since the sine of 90 minus theta is the same as cosine, I get this. And now that is the equation for the length of the bar as a function of theta. And if we're trying to maximize this function, we want to take the derivative of it and set that derivative equal to 0.
Okay.
Now, it's a little tricky taking the derivative of that because, like I said, we don't, I guess I could use the quotient rule or something like that to take the derivative of that. But the easier way is to convert that to where the trig function is in the numerator. So that is 9 cosecant of theta plus 6 secant of theta. And we had a negative sign in there somewhere.
Yeah. Well, no, not till we take the derivative.
Ah, right. Yeah. Good. So that's L of theta. And now L prime of theta. Now that's where we get, because that's a negative, it becomes negative 9 cosecant cotangent plus, that's positive,
So secant
6 secant tangent. And we set that equal to 0 and we solve it for theta.
Okay. Yeah, that was really, I mean, I can look at the work online, but understanding how you get the optimization part is not the tough part of what the homeworks were like. It's actually getting.
Yeah, it's setting up the formula for the length of theta is really what it is.
Right.
In other words, this, once you do this, you've got the problem solved.
Right, exactly.
But it's also, understand that when you write that, it doesn't make any sense at the moment unless x and y are both functions of theta, and they are. In other words, if you look at triangle number 1 and triangle number 2, I can make x and y functions of theta. And that's how I get that for x and that for y.
Okay.
And then you have to do the reciprocals, and then you have to know the derivatives of the reciprocals, and then you have to know how to solve that. And wow, this is quite the problem, actually.
I'm telling you.
Yeah, no, it is. I think that I could have worked on this a long time without getting anywhere until you told me this.
Yeah, I mean,
once you gave me that, that was the clue.
This teacher's pretty brutal with her style, I guess. I've learned a lot, but there's also a bunch of this level of problems that
I tell you what, here, let me give you a really easy optimization problem just to make sure you can do the easy ones, because I do think it's important to be able to do the easy ones. I'm just going to give you a simple one. It's kind of like optimization 101. You have a house that you're going to put a corral on. And you have the total amount of fencing you have equals 1,000 feet of wood.
Is it
So
square feet or just
no,
feet?
this fencing is measured. You have 1,000 feet of fencing.
Okay, you just want to make
Okay.
sure. I'll make sure for the.
Yeah. And first of all, the way I'm going to solve this is I'm going to start by letting that equal X and that equal Y.
Right. Okay.
And then I know that the area as a function of X and Y is equal to X times Y. Correct?
Correct.
And then this additional information they give you always allows you to set up another equation. In other words, if I have 1,000 feet of fencing, then I know that 1,000 equals 2x plus y. You see why?
Mm-hmm. Yep.
Because I don't need this side. I just need that amount of fencing, that amount of fencing, and that amount of fencing. And this second equation allows me to change the first equation to a function strictly in one variable.
Exactly. Yep.
So if I want the function as a function of x only, then it's going to be 2x plus, and what is y? Y is 1,000 minus 2x. So there's my area function strictly. I got something wrong. What is it? 1,000.
I think that's right.
It looks right, but the x's are going to cancel out, which is not what I want. Let me think about this for a second. What have I done wrong here?
I think the setup should be area squared, whereby you would be dividing over one of the variables, not subtracting.
Yeah, but you use this equation to solve for one of the variables to substitute back into that equation.
Right, right.
So if I solve for y, I get y equals 1,000 minus 2x. So now I have the area. I multiply. I added it instead of multiplying. Yeah, the area is x times y. So it's this times that. So now it's 2,000x minus 4x squared.
Okay.
That's the area function as a function of x. And now I'm going to take, this is always the pattern. So if you're trying to learn optimization, you want to follow these steps, which is to set up the function that you're going to optimize, the area.
Right.
And it's to use the other information to turn one of the variables as a function of the other variable. And I've done this by the time I get to that step. So now the next step is always to take the derivative, which becomes 2,000 minus 8x. With me?
Okay, yeah.
Going to set that equal to 0. So now I have 2,000 equals 8x, and x equals 28 goes into.
Why isn't the derivative, it's 8x? Wouldn't that end up, when these both get you just a flat number?
The derivative of that is
Oh, that's
2,000.
8 squared. That's 4 squared. Yeah.
And the
Sorry.
derivative
Sorry.
of that is 8x.
Yeah. I'm sorry. I didn't see the squared.
Okay. So I was able to solve for x so that I know that when x is 25, excuse me, 250, off by a factor of 10. Now I know the dimensions because I have 1,000 feet of fencing. If those are 250, that's 500.
Right.
And that is the maximum area you could build a rectangular corral with 1,000 feet of fencing. And this problem comes in various forms. A lot of times there'll be a river and they'll want to build a corral where the animals can get to the river. So you're still dealing with a three-sided rectangle that you need to optimize that area. So it doesn't really matter if it's on the side of a house or next to a river, it's the same principle. And this really is like the textbook optimization program or problem to teach you how to do a simple optimization problem.
Yeah, the squares, the anything with rectangles and area and whatnot is not so bad because for
No,
me it's easy to imagine it in 2 dimensions,
yes.
right? So that's
The
pretty
only
simple.
reason I brought this up is because this is the most likely kind you will see on a test, not the one you just showed me.
Well, that's why I showed you that one though, Mr. Cohen, because the
Yeah,
related rates problem that we had on the last exam was
yeah, it's a
harder than
similar thing. You gave me like the hardest one I've seen in a long time.
it was such a hard problem.
Yeah,
I
and
got it
related
wrong.
rates really aren't that hard either. It's
Yeah,
setting up the, in other words, always the one clue I can give you is that when you're setting up the original formula, that's what you're trying to optimize. They want you to optimize the area. They want the maximum area. So you need the area function. And in this case, it's a function of two different variables. I wouldn't be able to go anywhere if I didn't have this information up here about the total fencing, because the total fencing allows you to write y as a function of x,
right.
which means I can write the area completely as a function of x. And then I can differentiate it with respect to x. And then I can solve for x. And once you solve for x, you, at the same time, basically solve for y. But this is, if I were to guess, you'd get a problem more like this on your exam than the one you gave me.
I'm gonna pray, but if history has shown me anything, it's not gonna happen.
Yeah.
She's pretty brutal about her exams.
She likes her theta problems, doesn't she? Because this doesn't
uh,
involve any theta, and the same thing with your related rates. That was a theta problem. And
yeah,
most people have difficulty with theta problems because they just do. In other words, it's much easier to analyze a problem that's just got X and Y in it, no angles, than to have to deal with the trig functions that come with theta problems. But it was a good problem. I like it, actually. It was just a degree of difficulty that was pretty high. And I don't know, she might give you that. I don't know. She might give you two problems. One would be easy like this, and the other would be a harder one. The real secret was in drawing the picture. Actually, there is something common to both these problems, and that is the area of my corral is a function of two different variables, and the length of your pipe was a function of two different variables, X and Y. So that's the first thing you need to do, is to define it as two variables, and then hopefully you can define one variable as a function of the other. And we were able to do that. We were able to define both variables as a function of theta. And once you've done that, now you have a length of pipe that is nothing but theta on the right side. It was 9 over sine theta plus 6 over cosine theta. And you can differentiate that. It's not that easy, but you can do it. And then you can solve for it. And then you can set that equal to 0 and solve for theta. So it's kind of the same principle. I guess when you're looking at optimization problems, they usually do start out with two variables like that. And it's just that one of the variables can be defined in terms of the other one.
I think it was good to go over the more simple one. Definitely.
Yeah, no, that's always where I would start.
I really suspect that her question is going to be a degree difficulty more, just based on what I've seen so far. So it's unfortunate.
Let me give you a little bit of a clue here that is not always obvious. If you have a certain amount of lumber and you want to build the maximum square footage in a square or a rectangle, you will find that the maximum always is a square if you need all four sides. You'll notice that when we had the corral on the side of the house, this ended up being 2x, that was 2x, and that was y. So that is a rectangle, not a square. And that's because we only need 3 sides of it. But whenever you have all 4 sides, your answer better be a square.
Okay.
Or a circle. If I had a certain amount of fencing in the real world, in the cowboy world, they don't build square corrals. They build circular corrals. Why is that? Because that circular corral with a given amount of fencing is the largest area you can make, is circular.
Okay. That makes sense. Mr. Cohen, I appreciate the time going over this.
Yeah, you're welcome. I'm glad you have little tips for me on some of the more difficult ones.
Well, yeah, I mean, that's how I answered the homework question. But the problem is that doesn't teach. I don't understand. Like, that gets me the answer, but I don't understand how I get to that.
Yes, answer, absolutely. Right? That's what you need to understand.
I've explained to the professor before. I'm like, on some of these questions, I'm having to look up the answer, which I debate: do I get the points for the homework, or do I lack the understanding of the content? Yeah. And she gets that, she understands, but sometimes I think that it's kind of overkill with the level of question, but
it is. It absolutely is.
I digress.
And part of that is probably an ego problem of the professor. She's not trying to teach you calculus. She's trying to prove how smart she is and how difficult she can make problems.
My dad actually said the same thing. There's something to that.
Yeah, if you were teaching somebody calculus, you would never start there. You might finish with a problem like that, but you wouldn't start there. That's just unbelievably difficult.
It's kind of silly. I agree. So
yeah.
But anyways, I'm gonna do a little bit more review. I imagine this will be it. So finals is next week, so I'll probably do some more review of the entire content. So that will be things from like limits of infinity, limit difference.
Yeah, no, that's good.
The whole shebang. And then that'll be that. And then next fall is Calc 2. So I imagine that I'll be
that'll take you into these harder integration techniques.
Yes. I had the teacher send me the curriculum, or at least the topics of the
Mhm.
curriculum, and it's there's the techniques of integration, power series.
Yeah.
Um,
The first technique is integration by parts. That'll drive you crazy. And that's what's coming up directly after integration by U substitution, is integration by parts.
okay. Well, like I said, I'm gonna hold off and table that until I'm actually dealing with it. I actually over the summer wanted to try to maybe get a feel for it as well, so I don't feel so overwhelmed. But yeah, one step at a time, one day at a
Yeah.
time.
Yeah.
All right, Mr. Cohen. I
All right,
appreciate you as
Connor. Have a
always.
good one.
You as well.
Bye.